Okay, so speaking of fitting a normal distribution to an observed distribution. Suppose x is a continuous random variable follows normal with mean mu and variance sigma square. These are the two parameters of normal distribution. We know normal distribution is symmetric about mean mu and it is a bell-shaped curve. The PDF of x is fx 1 by root over 2 pi. PDF means probability density function 1 by root over 2 pi into sigma exp minus x minus mu whole square by 2 sigma square. Here x lies between minus infinity to plus infinity. Okay. So since here mean is mu, so normal distribution is symmetric about mean mu and is a bell-shaped curve. Z, which is a standardized form of x, that is x minus mu by sigma, this follows normal 0 1. This is called standard normal distribution. We denote capital phi z is a CDF of cumulative distribution function of standard normal distribution. This is equal to probability z less than equal to small z. So we need this CDF of normal 0 1 because the standard normal table is available. Okay, so you can find this in biometric table or in your textbook. Generally, these jet rounded in two decimal places. For example, if generally jet is two decimal places, 0.75. Actually, like table like first I discussed this part. Suppose some book denote this jet tau or z. So suppose z equal to 1.51 and the corresponding phi z 0.12758, or this may be a four decimal places. Okay, 1.52 equal to 0.12566, etc. Generally, in table, if you see that this jet start from zero point 0, but it is but jet may be negative. Okay, so if jet is negative, this is 0.5 because standard normal distribution mean of standard normal distribution is 0, and we know that the normal distribution is symmetric about mean, so standard normal distribution is symmetric about 0. So that's why this probability z less than 0 should be 0.5, or probability z greater than 0, which is again, that means I want to say z less than 0 equal to probability z greater than 0, it should be 0.5. Okay, and if z is negative, we use this relationship, phi minus z equal to 1 minus phi z. we knew all these things. Okay, so I assume that you know all this result 5 minus z equal to 1 minus 5z, and uh, that regarding the table of standard normal distribution, z table, some z table or table of standard normal distribution. Distribution. Okay. So now come to the point to examine if normal distribution will fit an observed distribution. One has to find the expected frequency for different class intervals, and then compare the two series of frequencies. For different class interval, the expected frequency for the class interval x1 to x2, where x1 less than x2 is n is a total frequency, total observed frequency, into probability small xn less than capital X less than small x2. Okay. Now here x follows normal mu sigma square. But for finding this probability x1 less than x less than x2, we need to transform x to z. Then this is equivalently, we can write this x1 minus mu by sigma by sigma x minus mu by sigma less than x2 minus mu by sigma. Okay, so this is okay. So this is equal to n into this is equal to n into pi x2 minus mu by sigma minus pi x1 minus mu by sigma. Okay, so if mu and sigma both are known, then first we compute x2 minus mu by sigma, x1 minus mu by sigma, and then using z table we find this expected frequency. If mu and sigma are unknown, then we estimate unknown or not specified. We first estimate these by method of movements, that is equating mu and sigma with the mean, this is a sample mean, x bar, and sample standard deviation s respectively. That is estimate of mu we denote by mu hat, which is equal to x bar, and sigma hat is equal to small s, where small s is a sample standard deviations, which is equal to capital N 1 by capital N minus 1 summation xi minus x bar whole square into fi from 1 to k. Suppose if there are k classes, okay. So and the x bar is 1 by capital N sum over xi fi I from 1 to k. Now I consider an example. Fit a normal distribution to following data on height in centimeter and comment on the goodness of fit. So this is the class interval. This is the lower limit. This is the upper limit of the first class. This is for the second class. This is for third, fourth, fifth, sixth, the last. And observed frequencies are, I denote this by small f, 2, 5, 20, 42, 39, 17, 4, think this is a 2, 5, 20, 42. So there is a miss. Okay. Please add one more class, that is one after 155 to 159. Add one more class, that is 160. No, it is one. This is 164. Okay. So please change this portion. This is 164. So corresponding frequency is 39. 165 to 169, corresponding frequency is 17. 170, 174, that is 4, and 175, 179, 1. And total frequency, that is 130, which is denoted by capital N. So now the class mark x, this is the mid value, 140 plus 144 divided by 2, that means 142, 147, 152, 157. So first class plus lower limit plus upper limit divided by 2. The formula is lower limit plus upper limit divided by 2. Okay. So then this is 62, 60 plus 164 divided by 2. This gives 162. Similarly, this is 167, 172, and last one is 177. For computation purpose, we change this x to y, where y equal to x minus 157 by 5. This is a 157 is a location and 5 is a scale, and 157 is a middle portion of this class. Okay, if you look at this portion, you see that 157 almost lies in the middle. Okay, so now then y is minus 3, minus 2, minus 1, 0, 1, 2, 3, 4. Now compute y into f, which is equal to y into f is minus 6, minus 10, minus 20, 0, 39, 34, 12, 4. And total is 53. This is equal to sum of yf. Now y square f, which is equal to 18, 20, 20, 0, 39, 68, 36, 16. And this total is 217. It is sum of y square f. Okay. Now x bar, this is equal to, we know this relation, if y equal to c, x is equal to c plus dy, x is equal to c plus dy, then x bar equal to c plus dy bar. So here c is 157. Okay, and d is 5, and y bar is 53 by 130. This is equal to 159.04. Okay, now ss square, which is equal to 25 sy square, because in again you know this thing, if x is equal to c plus dy, then ss square is d square sy square. So this is using this formula, we get this almost equal to 37.5758. Please check this. Okay, so sx approximately equal to 6.13. You just break this thing in that way. 1 by n minus 1. This is equal to sum over xi square fi 1 to n, 1 to k minus capital N x bar square. So here sy square, this is equal to 1 by 129 into sum over yi y square f, and here k is 1 2 3 4 5 6 7 8. K is 8. Okay, so minus capital N is 130 y bar square. So first you compute this part and put it here, and then you get Sx, which is approximately in my calculation 6.13. Please check. So now we construct the following table. So these are the class boundary. Okay, lower limit of the class boundary. So if you look at these are the class interval. So we know the formula of uh, convert class interval to class boundary. Just take consecutive two classes. Suppose I consider here first class and second class, and take the lower limit of second class, that is here it is 145, and upper limit of first class, that is 144. So and divided by 2, so this gives 0.5. And now for first class boundary, we lower limit minus 0.5 minus dash, sorry, this is dash 144, upper limit of class interval plus 0.4. So this is the 139.5, 144.5. So this is the first class class boundary. Similarly for second class boundary, this should be 145 minus 0.5, this gives 144.5, and one upper boundary is 149.5, because 149 plus 0.8, which gives 149.5. So and so on, we can easily convert using this formula. Just take a two consecutive class interval and uh, take the lower limit of lower limit of the second interval and upper limit of the first interval, and subtract this and divided by 2, and consider this result resultant value, that is, here it is 0.5, and take the any class interval, lower limit minus 0.5, upper limit plus 0.5, this gives you the class boundary. Okay, so here in this table, instead of considering class interval, I consider class boundary, because class boundary is a continuous. These are the upper limit. Okay, see that 144.5 is the upper limit of the 144.5 is the upper limit of the class boundary. Okay, 149 is the upper limit of the class boundary, and so on. So then next part is 159. Just add 5, because width of the class interval is 5. You get all upper limit of class boundaries. Last one is infinity, because x lies between minus infinity to plus infinity. Now z score, this which is equal to x minus x bar by sx. So when x is 144.5, then we get these values minus 2.37. Please check my calculation. This is 1.55. I just tell this thing. This is equal to 144.5 minus mean is 159.04. X bar is 159.04. So I write this thing here, and Sx is 6.13. This gives minus 2.37. Similarly, we get corresponding this corresponding 149.5, jet score of 149.5 is minus 1.55. Similarly, jet score corresponding 154.5 is minus 0.74. The score of this value is 0.07, 0.89. Jet score of this value 1.71. This is 2.52, and last one is infinity. So now, using jet table, we compute phi z, and z phi minus infinity, it should be 0, phi minus 2.37, because jet table consider value only from 0 to infinity, 0 to, I think, 0 to 4. Okay, maximum table consider z value 0 to 4, because if you know why this is, because if you see the empirical rule, because the empirical rule is perform well for Bell-Shaped distribution, and and for normal distributions, we know 99.7% of data lie lies within -3 to +3. Okay, -3 to +3 for Z score. So after that, very little portions exist. So generally, most of the table consider maximum 3, or some books consider it is 4. After 4, if you look at the value of 5 4, it almost goes to 0. Okay, so uh, jet table generally considers 0 to 4. So 5 minus 2.37. For this, we first change this value 1 minus 2.37. Now look at 2.37. When z equal to 2.37, first compute phi 2.37. I repeat this portion again. When phi equal to, for computing phi equal to 2.37, just go to the z table. First find z equal to 2.37. Suppose then go horizontally corresponding 2.37, find phi equal to 2.37, and using this phi 2.37, 1 minus phi 2.37 gives phi minus 2.37, which is 0.0089. Similarly, for this value, we use same process and get 0.60506. Okay, so please check these values. 0.2297, 0.07, this is 0.5279, 0.89, which is 0.8132, sorry, 33. Okay, 1.71, this is equal to 0.9564. By 2.52, this is equal to 0.994133. And phi infinity, it should be 1. So now we interested in the interval. Okay, so this interval 142, what is the expected frequency of this interval 142, 144, or 144, 139.5 to 144.5? Similarly, what is the expected frequency of 144.5 to 149.5, so on. But here phi z gives the probability, phi z gives the probability less than equal to x. That means the, the probability that x less than minus infinity, probability that x less than 144.5, probability that x less than 149.5, probability that x less than 154.5, and so on. So for this reason, we compute phi z delta. This is a or this is an operator. This means this is the difference between two consecutive values, larger to smaller. So 0.089 minus 0, this gives, so 0.08, 0.0089 minus 0, So this is 0.0089. This means x less than equal to 144.5. This is this difference 0.0606 minus 0.089. This is equal to 0.0517. So this means x lies between 149.5 to 144.5. This, I repeat this part again. This probability means probability that x lies between 144.5 less than x less than 149.5. Okay. So similarly, 0.2297 minus 0.060, this is equal to 0.1691, 0.52279 minus 0.2297, this is equal to 0.2983982. Sorry. So please check my calculation. I repeat again, please check my calculation. This is 0.8133 minus 0.5279, which is equal to 0.2854. This is 0.9564 minus 0.8133, which is equal to 0.1431. Similarly, this is equal to 0.9943 minus 0.9564, which is equal to 0.037778. Okay, I think 79. Okay, 79, and this is 1 minus 0.9943. So this is equal to 0.0057. So this is called forward difference operator. Is delta, capital delta. This is a forward difference operator. Now, expected frequency, that is equal to capital N into del phi z, which is equal to, here capital N is 130. So 130 into 0.0089 is almost 1.156. I approximate this by 1 because frequency is always integer. 6.718, which is approximately 7, 21.798, which is approximately 22, 38.773, which is approximately, okay, Shayok, if phi z, please wait. After computing this thing, I will address your question. 37097, which is approximately 37, 18.603, which is approximately 18, 4.909, that is 5, approximately 5, and 0.763 is approximately 1. Okay, Shayok, can you tell me, you need the explanation? Do you need the explanation of phi z or delta phi z? Phi z or delta phi z? Are you hearing me? Please tell me which one you need. Phi, delta phi z or phi z? Please tell me. Okay, phi z. Actually, if you look at the standard normal table, is okay. I will give you some values. First one, okay, phi z. Okay, standard normal value generally start from in Z table is starting from 0, 0.01, 0. Yes, of course. Otherwise, you can use your book 0 to, and up to it is some book gives 3 or 4. Okay, here I just use 0.0 to 3.2. Why 3 or 4? Because after 3, value of phi z is almost like close to 0. Why? We know the empirical rule. Empirical rule says 99.7% of data lies within mean minus 3 SD, mean plus 3 SD. When for Z score, mean is 0 and SD is 1. So for Z score, it should be minus 3 to plus 3. Clear? So most of the table consider the Z value 0 to 3. Why they didn't consider negative portion? Because if you look at the normal distribution, standard normal distribution, which is symmetry about mean 0, suppose you want to compute this minus z. So probability capital Z less than equal to minus z, which is equal to capital phi minus z. Because of symmetry, you get a z here. Because of symmetry, this portion, this shaded portion, these two shaded portion are same. So this is again same as z greater than small z. Because this is a continuous, so whether you give equality or does not give, it doesn't change this probability. That means I want to say probability z greater than small z same as probability z greater than equal to small z. Okay, so this is equal to 1 minus probability z less than equal to small z, which is equal to 1 minus 5z. So if you know the positive portion, so automatically you can calculate using this formula the for the negative value of phi z. Okay, for negative z, you can easily compute phi z. For example, if you look at this table, so the table is like that. Okay, suppose you want to compute minus 0.02. So 1 minus phi 0.02 from this table. first you go find out the value 0.02, then go to the go horizontally and find corres- corresponding z equal to 0.02, find phi z. Here it is 1 minus 0.5080. So this is equal to 0.4920. Okay. So this is the value of phi minus 0.02. In that way, you can compute phi z where z less than 0. Otherwise, for positive portion, suppose if you want to, uh, there is, I consider another value. I consider another value from the table 0.35, 0.50. Okay. So, our corresponding phi z is 0.6915. So, suppose you want to compute 0.5, 0.5. So, first you find that z, from the z table, you find the z where z equal to 0.5 and go, and then you find this 0.5 and then go horizontally and find phi z corresponding z equal to 0.5 and which is equal to 0.6915. Okay, so in that way we can compute phi z. So please tell me, Shahrukh, have you any trouble? Still have you any trouble? Please let me know. So in that way we compute the expected frequency. This is the expected frequency, and observed frequency is here. So observed frequency is here. Thank you, Shahrukh. So observed frequency is here. That is 2, 5, 20, 42, 39, 17, 4, 1. And we see that comparing, we see that after comparing expected frequency and observed frequency, comparing expected frequency with the corresponding observed frequency, we conclude that the fit is good. So please tell me, have you any queries? Otherwise, I end this thing. Okay. Have you any queries? Please let me know. Otherwise, I end this thing. I will discuss your a practical problem on intra-class correlation coefficient in my next class. That will be on Monday. Okay, and after that, I will take another class in Monday on scaling up a data. Okay, so please let me know. Have you any problem or queries? Okay, thank you. So thank you. So we'll meet again on Monday. Thank you everybody for watching this video.